Okay, so let's start. Welcome everyone to our 5th webinar organized by EUROfusion, so webinars on GPU programming. Today we have Dmitrii Tolmachev from Forschungszentrum Jülich, and he will present us Vulkan Compute, an introduction to the fast cross-platform and open source GPU API. So we'll have first a presentation session, then a quick question session, and we will go through a code demonstration session. So please, Dmitrii, you can start. Thank you very much.
Hello and welcome to everybody. Thanks for inviting me. So this presentation will be on Vulkan Compute. And to outline the presentation, we'll start with explaining what a modern GPU is. And after that, I will talk about the factors that can limit GPU performance, and especially cover the memory-bound problems and how to avoid bottlenecks in them. Then I will briefly describe what Vulkan Compute is and what are its main advantages. For example, it's really fast, it's cross-platform, and it's open source. So this sounds really interesting, and we'll talk about it in detail and have a coding session after the presentation that will show a real-world scientific example of this. But before that, I will briefly describe my previous work in Vulkan Compute and what really makes it as a good API for scientific computations. So I have created a Vulkan fast Fourier transform library, which has a performance similar to NVIDIA's EUROFFT, and which is also like following the Vulkan Compute advantages by being cross-platform and open source. And then I will talk about the application of this fast Fourier transform library and how I used it to create a scientific micromagnetic and atomistic spin dynamics solver which uses GPUs, and compare it to the already existing code in CUDA. And after that, I will briefly show you the example of Vulkan application and what it takes to actually create it. So the modern GPU architecture follows the single instructional multiple data configuration, which actually just uses a lot of cores and a warp scheduler, which issues commands on them. So warp scheduler gets 32 threads and executes one instruction at them at one point of time. So you need to program your code accordingly so that your data is used in a way so you do a few amount of instructions, but on a large scale of data. Here you can see the streaming multiprocessor or compute unit of an NVIDIA A100, the newest GPU, and it has like 108 of the depicted units, where each unit has a lot of cores. For example, it has 64 floating point 32, which is a single precision cores that do single precision operations like addition and multiplication. And then it has 32 floating point 64 cores. Well, for consumer level GPUs, there are much less double precision cores, but we are talking about a scientific one, so it should have double precision support. Well, it follows a similar structure to the processors, so it has caches, but they are used for different things. The processors caches and the CPU caches are used to actually like have data store them for faster access because the bandwidth of the CPU is not that high, and for GPU the bandwidth is really high, but latency is really like high also. So you need to schedule your requests and ask for a lot of data, and the way you schedule the request, it takes time on GPU, and on CPU you schedule your requests much faster, but you also can get a lower amount of data at the same time. So there are also a cache structure, L2, shared memory, and then there is a register file which cores can use to actually perform computations. So as I said, a warp scheduler can schedule one command at a time to 32 threads, and this is like very important to like understand how GPU works. And as you see, the shared memory is located also on chip, and this is some fast memory that all threads have access to. And in computer tasks, it used to communicate is used as a communication buffer between them. Okay, so the GPU memory bandwidth, as seen here, is 1.5 terabytes, and we'll see like why this value is really important on the next slide. So there are two types of problems that can be encountered in GPU programming. First, well, it's similar to the CPU programming. First, there are compute-bound problems where GPU is bottlenecked by how many operations it can perform. And then there is a memory-bound problems where GPU is bottlenecked by how much information it can transfer. And this covers the bandwidth value we have seen on the previous slide. So it's fairly easy to distinguish them. If you're compute bound, you get a high GPU utilization and low bus load. And if you're memory bound, the GPU is just transferring data, and then all your cores are not doing much and just waiting for the data to transfer. So it has a low GPU utilization. And depending on the parameters, a problem can easily change between them. So for example, on a consumer level GPUs, there are not that many not that many double precision cores. So if you want to do something in double, the performance can really degrade. And if program was memory bound in single, it can easily become compute bound in double. And this is the case for FFT as well. So the memory bound problems are often caused by not following the design rules of the GPU architecture, which are really important. And this is what I really want to talk about and like specify how this can be solved. So there are multiple bandwidths inside the computer that can happen, and each of them have a different speed. So if you want to transfer data from the CPU to GPU, if GPU has a dedicated video memory, it will transfer through the PCIe bus, which is on PCIe 4 is something close to 64 gigabyte per second, which is really small compared to the speeds GPU can get between the VRAM and its L2 and L1 caches, so basically the chip memory. And this can reach like 1.5 terabytes on the fastest GPU available, which is the DGX A100. But this has a high latency, and there are multiple techniques that GPU vendors use to alleviate it. And then there is on-chip bandwidth, like accessing a register file or L1 cache and shared memory. And it has a really high bandwidth and really low latency, and it's limited by the thing that there is just like a few amount, like 256 kilobytes of register file available. So to program good GPU code, lowest possible memory transfers are needed. So the GPU bandwidth is really high. So you would like to have as few as possible CPU GPU transfers and know if possible. No, of course, you can get some asynchronous downloads from the GPU, but remember that the 30 gigabyte per second is a really limiting factor in this regard. You want to minimize the GPU VRAM to the on-chip memory communications, and then you want to optimize the fastest available on-chip memory usage. Note that you need to maintain the occupancy so that your program still is memory bound, and you can actually use the free resources to hide the latency of the communications. Otherwise, it can really become the compute bound problem. Okay, now I will talk about the problems that can be encountered in GPU programming and that are kind of easy to fix, but you need to know that they exist to fix them. So first one is memory coalescing. When you upload your data from VRAM to the on-chip memory, you are actually transferring it in chunks. So you're not transferring it one float at a time. You transfer, for example, 128 bytes if you request an L1, L2 cache, and 32 bytes for request to global memory on NVIDIA GPUs. So this 32 bytes actually can contain 8 floats at the same time, because each float is 4 byte. So if your threads in the wrap access successive aligned bytes, for example, here you see the first 8 bytes in address, first 8 bytes in the memory, this transaction can be performed in one transfer to the GPU. And even if the threads access the shuffled data, which is still aligned by 32 bytes, well, this is also good, and it's also done in one 32-byte transaction. But if you try to access a misaligned data, which has like data from different blocks, or you want to try to access like each thread tries to access a different block of data, well, you will have to deal with at least two 32 bytes transactions in this case. And like if you access 8 different locations in the GPU memory, this will take 8 32-byte transactions, which limits the bandwidth by 8 times. And this value is really like vendor specific and GPU specific, and also depends on the cache type. So for example, on Intel and AMD, as far as I know, it's 64 bytes per access. And on NVIDIA, before Pascal generation, it was 128 bytes for all the requests. So this is something you need to keep in mind so your code doesn't bottleneck and use bandwidth fully. Okay, so when you use shared memory, you also can get conflicts of memory, which can really slow your on-chip performance. So shared memory is an on-chip memory which is accessible by all threads in the warp. So if a warp wants to get values from this shared memory, there are some strict rules you need to follow. The memory is divided in banks, and each bank can be accessed separately in one request. So for example, if you have 16 banks, the addresses 0, 16, 32, and so on will correspond to one bank. So if you actually try to access this bank by all threads, for example, and you access different values in this bank, the access becomes serialized and you get your performance hindered by a lot. And if you want to access like 16 consecutive numbers, which will correspond to different banks, this will be done in one request, even if it's like shuffled. So you need to know how your data is stored and try not to access the data that correspond to one bank. And this also like can increase the speeds and make your code much faster. Okay, now we will go on to the actual Vulkan computing and how you can do stuff in it. And first we will compare it to existing APIs, for example. Usually people just use CUDA and nothing else is really known in the compute world except for maybe OpenCL. And CUDA is really good because they have developed their infrastructure for a long time. And like you get a low-level support, a good driver support, and it's really easy to use. But it's not cross-platform and it's not open source, and this can limit stuff, as I will show later. And then there is Vulkan, which is a relatively new API, which is like developed by the Kronos group that also developed OpenCL and OpenGL. And it aims to like, it's mainly used for gaming industry, but it has a good share of compute capabilities. So you can actually like do extremely low level stuff and get a cross-platform and cross-platforms code and which has comparable speeds to CUDA. And it's also future-proof because it's backed up by gaming community. Well, you may ask, why don't just use OpenCL, because it has been also for some time. Well, OpenCL had really big driver issues. So like there were like no good support for OpenCL 2.0. And for the past 4 years, there were like no news on OpenCL if it will be even supported. Well, there were news that there is going to be OpenCL 3.0 released recently, but we will get to see if it's any good or they will just go back to the old thing they were like a couple of years before. Then there is also an OpenGL, which is mainly, which is really old and like mainly used for graphics. And there are also some notable mentions like Rock'em and Heap, which is developed by AMD, and then Direct Compute, which is developed by Microsoft, and Metal, an API that is used by Apple. And then there you can use high-level infrastructure like OpenACC, SQL, intermediate representations like IRE and MLIR. But we won't cover them in this talk. We will just mainly focus on the GPU side and low-level stuff. So Vulkan Compute, why it's good? Well, it's a low-level API where you can get a good share of control over memory management. And as I said before, memory management is really important on the GPU. And it's modern API, and well, it's like developed for recent compute developments. It has the experience of CUDA, like because it was developed only 4 years ago. It has low CPU costs because you can do stuff in parallel there, and it's open. It's cross-platform and open source. Well, it works on NVIDIA, Intel, and AMD, and mobile devices. And the code I am going to show you later on will be launched on the NVIDIA, Intel, and AMD GPUs. Well, it's open source, it's maintained by community, and you have the full control over what's happening there. It has good driver support because the gaming industry is like really fueling it, and this is also contributing to it being future-proof. Okay, now I will briefly describe what I have created in Vulkan during my master thesis. The first thing is a GPU library for fast Fourier transforms. It's used in many scientific fields. I used it for dipole-dipole interaction in magnets, but it can also be used for convolutional neural networks and in machine learning and signal processing. So it's really important library, and there was no good library in Vulkan for fast Fourier transforms. So I mainly used it for convolutions via convolution theorem, which like represents a matrix-matrix multiplication in frequency space. And in single precision fast Fourier transform is a memory bound problem on GPUs, which we will also cover later. And this is why I described all the memory optimization techniques before that, because they're really important in designing the GPU application. So it's cross-platform, it's header-only library, and it's already available on GitHub. And recently, people implemented it as a part of a Forschungszentrum benchmark, which I will show later on. So the things that VK FFT supports right now are pretty common for fast Fourier transform. The main like limitation is just that it's only power of 2 systems that were optimized yet. But everything else is like what you would expect from a complete fast Fourier transform library, like big with dimension sizes support. It's being using in-place transformations, which is like a slowest memory amount of as possible as you can get. It has real to complex, complex to real transformations. It has convolutions and has a native zero padding support to model open systems, which I will briefly describe later on. These are like really good memory saving techniques that can be used not only in fast Fourier transform, but in other software too. And it has single, double, and half precision support as well. To like show results straight away, here's a comparison of VK-FFT on the GTX 1660 Ti, which is like mid-range consumer level GPU. And as you can see, it's like really close to CUFFT in the smaller systems, and in bigger systems, sometimes it even beats it, like up to 20% here, which is done by the memory saving techniques I will explain later. And you can test it as well on your own machine by downloading the code. Okay, so it's part of Forschungszentrum benchmark, and here you can see like how it scales the GPU. Like, for example, it can be run on Intel, it can be run on AMD, and you get their results like compared to their actual power rankings on some other websites. It's like really similar in this regard. Okay, why it is able to compete with CUFFT? Well, as I described previously, it has as low as possible memory transfers amount and maximum GPU bandwidth utilizations. There is a technique on register file utilization that I will briefly touch later on. The in-place transforms are optimized, and the real to complex and complex to real are also optimized. Well, these are optimizations that are needed in any FFT library if you want to like have a good library. There is a convolution merging with the last step of fast Fourier transform, and there is a native zero padding, which I will describe right now. And you can also merge consecutive iterations because Vulkan has low level support. This mitigates the dispatch call overhead. So the typical memory layout of fast Fourier transform is like you do a fast Fourier transform over the x-axis, then you do a transposition, which can be done in coalesced memory and coalesced axis. Then you do again the transform over the x-axis and do transposition again. Why it's good? It's because it has always a coalesced memory access. You always transfer this 32 or 64 bytes of data and never rely on like actually doing strided access, because here there is a lot of data here and the accessing of 0, first and second element is really strided and you get like really reduced bandwidth. And the transposition can be done in a coalesced way. So why it's bad is because these transpositions are like 2 additional memory transfers to the on-chip. So instead of 3 transfers, you have 5. And this can really hinder the performance. And now the memory layout I use is kind of good in this regard because it only has 3 memory transfers and doesn't do any transpositions. How I am able to coalesce the memory in these regards. I upload nearby FFTs in a coalesced memory way group. So like one chip performs multiple FFT sequences at the same time. And this allows to get the coalescence in x-axis and group them. This thing can be like transferred to any other GPU programming code, and I think it's something really interesting, so people should try it out. Well, this actually limits the amount of the size of FFT which can be done in one upload because you can only upload 4 sequences to the shared memory, and shared memory is limited by like 48 kilobytes on NVIDIA in one static allocation. So I used only 32 kilobytes, but this can be alleviated by a 4-step FFT algorithm. And these uploads can also be done if you have strided data in x-axis. So for example, you have a 4-step FFT which like uploads different sequences which can be strided in this axis also. So this technique can be like elaborated a lot as well in the future, and I will probably make some sort of publication on this topic. So the register file overutilization is a small technique that just says that your register file is usually much bigger than the available shared memory. And if your problem is extremely bandwidth bound and you don't really do much computations, you can use shared memory as a communication between the registers, just like you do in OpenMP system. And this way you can upload a sequence of 16K in one upload to the chip. And this is something like really cool because you get your own you get your own data transfer and data communication problem like you would get in big cluster, but it happens on chip in one compute unit in a real small fashion. So this comes at, of course, at the cost of reducing occupancy. So for some compute bound, so for some problems, it can switch the problem from memory bound to compute bound. And then there is native zero padding, which is something I'm really proud of. So if you do a zero padding of a system in the fast Fourier transform, then you can basically kill the circular part of a fast Fourier transform, and the system becomes an open system. So it's not periodic like it's here, but an open one. And how can you optimize it? You can basically omit data transfers of all these zeros and don't do the fast Fourier transforms of sequences full of zeros. And to do so, you need to have a full access to the fast Fourier transform code. And I don't think this is possible at the current EUROFFT implementation. And if you need to do this, you can if you can do this, you can really like reduce the amount of memory transfers and the computations, and get up to 2 times speed increase in 2-dimensional problems and 3 times speed increase in 3-dimensional problems, as can be seen here on this benchmark. So this system can be seen as zero padded in green and non-zero padded in the yellow. So if you just fill it with zeros and do a full Fourier transform not knowing that they are zeros, you will get these timings. Otherwise, you get these timings, which are like 2 or 3 times faster. So if you need to model an open system, you would really want to have your FFT implementation be able to do so. Okay, now I'll briefly describe a scientific software I created because we are running out of time. And I've created micromagnetics and atomistic spin dynamics of Spirit code that was already developed for CPUs and big clusters in the Forschungszentrum Jülich. And I have created a GPU version of it and refined it. So this is the system of differential equations we solve on a big grid of cells or spins. This is like an ordinary differential equation, which like every spin is communicating with other spins through a effective field, which are described as the all combination of a sum of combination of spin interactions. And this model just describes a higher scope model of a spin processing around this effective field. The effective field constitutes of multiple interactions like exchange, DMI, and isotropy and Zeeman. I won't go into detail there, but they are all like finite difference scheme that can be really easily calculated. And then there is dipole-dipole interaction that requires a convolution, which is done using fast Fourier transforms. I've also implemented some solvers in the Vulkan, which were also optimized according to the memory transfers. So there are velocity projection, conjugate gradients, and just direct integration techniques like Runge-Kutta. And here is a comparison, apple-to-apple comparison to the MUMAX3 code run on the same GTX 1660 Ti GPU. We use all the aforementioned techniques of fast Fourier transform optimizations. So the MUMAX3 is a CUDA-based code that was already developed for like 6 years and is commonly used in the field. And we try to compare it apple to apple to Vulkan Spirit because we use the same Runge-Kutta 4 solver, the same time discretization, the same open boundary system with dipole-dipole interaction, and we have the same time step. And I integrate for the same amount of time. And as you can see, the code in Vulkan can perform like 3 times faster on some systems in 3 dimensions, and like up to 2 times faster in 2 dimensions, which is really good and shows that Vulkan can be just as fast as CUDA-based code. So why it's able to compete with MUMAX3? It's mainly because of the optimizations I described before and the fact that I am managing memory very carefully and avoid all the possible bottlenecks there. And it also is because there are as few as possible GPU to CPU transfers, except for asynchronous downloads from the GPU. So you can also get this code on GitHub and play with it yourself. It has a cool graphic user interface, so you can actually see what you're getting in real time. And I would also want to state that it has no dependency on proprietary libraries, and you can get full access to the code. So the conclusion of this talk is that I briefly state that Vulkan can actually be used to create fast compute applications and used in real science. So I have created Vulkan Spirit, which is up to 100% faster for large systems and 200% faster for smaller ones, which can also be downloaded on GitHub as it's open source. And I've created a fast Fourier transform library, which has comparable performance to EUROfusion on small and medium-sized systems, and is faster than EUROfusion for bigger systems because of this memory layout I use for uploads. Then you can also optimize the VKFFT to your own task and implement something similar to native zero padding because their shaders and their code is freely available on the GitHub. And I encourage you all to check this out because the library has got a lot of attention and it's kind of refined for use by everybody already. So this is the end of the first presentation part of the talk. We can briefly have some questions now and switch to the compute part.
Thank you, Dmitrii. Guys, if you have any question, please unmute. Okay, Thomas, please unmute and ask your question.
Hi, Dmitrii. So maybe if you could go back to the table you have on slide 8.
Yep.
So I mean, in some sense, this table is maybe the key point. If I want to write an application, the second to last column is certainly one of the most important,
Yes.
if not the cross-platform one as well. And so let's suppose I want to write my application in SYCL, which for something that, I mean, what you could have added as an extra column would have been cross-platform, including a CPU implementation, right? And for OpenCL, you can have code which will also be able to run on the CPU. For SYCL, this is also handled nicely. So suppose I want to write my code in SYCL or OpenCL, then the question is how well do the frameworks interact with each other? So do you know if from one framework you can call code, so if I have a SYCL application, can I call Vulkan FFT, your Vulkan FFT library, for example?
Well, the SYCL as well as OpenACC and all others are higher level. They use something like CUDA or OpenCL as a backend. So there is some sort of connection between them. Well, as far as I know, SYCL uses OpenCL. I'm not sure if it's translatable to Vulkan, but it's probably possible to do so. And well, why not?
Maybe I rephrase the question. Suppose I have an OpenCL code. Can you then make calls to the Vulkan runtime during the OpenCL code, or is it mutually exclusive once the runtime has started?
Some people actually created some interoperability between OpenCL and Vulkan, but even though the OpenCL and Vulkan use the same SPIR-V binary representation, well, OpenCL uses a kernel model and Vulkan uses a shader model. So I'm just not familiar if you really want to do the interoperability in this case. But I think there are people who exploring this possibility.
Okay, thank you.
You can also find it on the internet.
Okay, guys, thank you. Any other question for Dmitrii before we start?
Maybe Leon, question for the OpenCL. Why would you say that it is not future-proof?
Well, because it had a lot of driver issues in the recent GPUs, and like NVIDIA didn't support the OpenCL 2.0, and Apple just specifically stated that they will use Metal, and I think the Apple was a big supporter for OpenCL in the beginning, and then they just dropped it. So I'm not sure about OpenCL, and there were like no releases before OpenCL 3.0, which was actually going back to the roots and like discarding most of the changes of OpenCL 2.0 as far as I know.
Yeah, but for Vulkan, that is somehow now future-proof. Would you find any statement that NVIDIA will rather support Vulkan as it was OpenCL in the past?
The main thing why vendors will support Vulkan is because it's used by gaming industry a lot. And the thing is, the modern Stadia machines, which are providing like cloud-based gaming, which is a really big field nowadays, they use Vulkan in all of their like implementations. So if in this case, the vendors want to support Vulkan, and NVIDIA is writing actually a big part of the Vulkan extensions. For example, there is a ray tracing extension, which is like port of NVIDIA's previously created extension in Vulkan, which allows to run ray tracing on basically any GPU.
Thank you. What about the, let's say, CPU extensions of using, as it is possible with OpenCL, with some CPUs to use some features of OpenCL, will that be also for Vulkan?
I'm not sure like what you mean by this. As I said before,
So that you don't need a GPU, but the GPU features as it is in OpenCL to be run on the, let's say, newest CPU.
I'm talking about GPU computing. And as I said later on about the memory things, which this memory like optimizations, they are true to the GPU programming. They are not the case for the CPU programming. And you wouldn't really want to run GPU code on the CPU without any optimizations. So I'm not sure. I don't like the idea of like mixing GPU and CPU code.
Okay, thanks.
If you want to get good performance on the GPU, you have to write explicitly for the GPU, unless you use some intermediate level representation like Lear, which does the stuff for you. But this limits the low level support you can get. And this can like limit the way how you handle your memory transfers, which can be really important on the GPUs, because for now the bandwidth is like limiting more and more like applications compared to the compute part of it.
Why are you adding OpenGL to the GPU compute frameworks? It is mainly devoted just by gaming industry that will be supporting, but this is purely graphics, I would say.
No, it's not purely. They still support compute shaders. Yes, they're optimized for graphics, but they can still be used for compute part.
But nobody does that, actually.
Well, nobody does that because everybody is doing CUDA. And nowadays, if you want to go low level, Vulkan provides a better low level support than OpenGL, as far as I know. And it has a better support for compute capabilities there.
Thanks.
Going back to the last point that you mentioned, for a library, it's perfectly reasonable to separate out a CPU version and a GPU version. But for any production code, this is surely an impossibility. You might have a slightly different tuned algorithm for one versus the other, but any framework which doesn't support CPU and GPU within the same code base, and this is the benefit of OpenCL or SYCL or some other routines. I mean, let me rephrase. How can you imagine Vulkan being used in a production-based HPC application when there has to be a complete duplication of everything for CPU and GPU?
Well, if you look at SYCL, I think they should have different backends for the CPU and GPU codes. So, for example, the VK FFT can be a part of it, which is run on the GPU, and then you have something similar written in the CPU code. So I'm not against using the code that can unify the GPU and CPU, but the coding paradigm is different between them. So if you want to write CPU code, you probably use different tools, and this is true for OpenCL as well. So if you use a GPU paradigm applied to the CPUs, you will get bad results. The same thing if you use a CPU paradigm to the GPU, you will also get bad results, because they can transfer at different memory rates, and GPUs are just optimized to do this as seamed instructions really fast. So ideally you have different codes for CPU and GPU, and after that you can try and do the SYCL, which will do some stuff for you. But at the backend, you would like to do them differently.
I completely understand having the libraries different. I mean, this is the same already if you compile against if you compile to a different platform, then you want to have the different native libraries, of course, for the FFTs or for the linear algebra routines. But if I'm writing my application code, there's the experience I think that most people have is that if you have 2 different versions of it for the 2 different platforms, that the sustainability of this is not very strong.
Yeah,
Do you
and
think that this is
that's
wrong
a hard
or
thing
not?
to balance. But if you like have one version, it will most certainly perform worse than 2 different versions.
Okay, but that's the whole aim of Cocos and SYCL and frameworks like this, is that they abstract the memory access for you, right? They change the memory access
And
patterns.
the more intermediate levels you have, the further you are away from the pure GPU or pure CPU programming. And this can't increase the speeds if you understand the paradigm really good.
Okay, I don't agree, but thank you for your comment.
Thank you. Any other question for the time being? Okay, I think nope. Thank you, Dmitrii, for answering all this question, and we can move to the second part of your talk.
Okay. Okay, here I have a small example application, which is also, I think, attached to the mail everybody has received. Well, I will also upload it because I've added a lot of comments to it, and it like describes the way the Vulkan application is structured. So first of all, you need to actually query for the support of Vulkan. You need to create an instance. This is a connection between your application and the Vulkan library. And I forgot to mention, but this code is written in C. But it can be really easily translated to C++ if you want to. So you create a connection between your application and the Vulkan library. Let's see what's inside this function. So you can pass some simple app information, which is not really interesting. You specify the API version you use, and you specify the extensions that you need. For example, you can specify debugging extension, which will just check if you are like invalidating some Vulkan guidelines, which are fairly strict. So you ask for a support, and then you like created your connection to the Vulkan library. After that, you can set up the debugging messenger, which will just output to the console or whatever, wherever you want the validation or errors which it can encounter. For example, if you like pass a buffer and like your shader or kernel doesn't have a slot for this buffer, it will report this. So you were passing something to the thing that is not expecting it. So this is like the validation and how it's done in Vulkan. Okay, after that, you need to find a physical device. The physical device is something you have on your system. For example, this is an Intel GPU, iGPU laptop that has Intel UHD 610. And this function will basically report the list of available devices and enumerate them. And then you can just specify in your application which device you want to use. You can either use like a device ID, like here, to specify it from the list. And you can also print it here if you want to see which like GPUs are available. After you've created the physical device, you need to create your logical device, which is a representation of this physical device in Vulkan. Let's take a look at this function. So you create your logical device. You create a queue family. You ask for a queue family, which is something you're allocating. You submit your command buffers to execute on the GPU, and you ask for some features that need to be enabled on this device. For example, if you need a flow like double precision support, you specify that this is true. You pass these features, and then the Vulkan will know that you need these features, and it will check if this feature is supported, and if not, it will report an error. And if you specify this feature, you can basically use double precision in the shaders. So after you've created the logical device, you need to create some other things like fences. So fence is something used for synchronization. Similarly, in other applications, it's like placed between the command dispatches on the GPU, so your command dispatch finishes before you can proceed with your code. And then you allocate a command pool. This is a place where command buffer memory is allocated from. And command buffer is basically a thing where you submit your commands, which will be executed on the GPU. You record it, and then you like send it to the GPU to execute on. Well, this is kind of similar to the CUDA programming, and although it's done in kind of different fashion, because in CUDA you do kernels, and in Vulkan you do shaders. So you need a special small program, which is like a GPU code called shader, which I can show you briefly, like this. So here you see a small shader which does a transposition on the GPU. And like it has two buffers, one input buffer and one output buffer, which it uses. Then it has some constant specified in Vulkan, which define the work groups, the work group. This is similar in kernel and how you launch kernels in CUDA. So for example, if this one uses tile transposition, so it's uploading the square system of 4K on 4K, 4096 on 4096, and it uploads it in tiles of like 16 on 16. So the 16 value is chosen so the memory is coalesced in transfers. So the 16 consecutive floats can be coalesced in 64-byte memory transfer. For example, on the Intel, this is like the lowest possible number you use to get the full bandwidth. So you specify this, like for example, this will be 16, this will be 16, this will be 1 as an input. And then you specify strides so you can read from these buffers with these strides. For example, this one will be 1, this will be 4096, and this will be 4096 multiplied by 4096. Then there is a push constants, which is here for just for example, because it's not really used. It's a small amount of data that you can specify before actually like submitting your buffer for the execution. This is a function which like calculates the index ID of data in the buffer. And then there is a shared memory allocation. So for example, you use a workgroup size on y direction, which is 16, and then you use a stride on the workgroup size x. And this +1 is really important because it makes the shared memory accesses it makes the shared memory access to have no bank conflicts, because if we have 16 banks and we have the size of 16, well, when you want to access the elements 0, 16, and 32, you will have the bank conflict and the access speed will be like 16 times slower. But if you have 17 elements and then you access the element 0, 17, 34, they all become shifted by 1, so they correspond to different banks. And we can launch this code with the +1 and without it and see how it performs later on. And here is like simple transposition technique. So first we get an ID, we get elements uploaded to the shared memory, which like correspond to the square buffer in the input memory, and then we do this transposition step. So we just write it to a different location on the output buffer transposed. And why we need the GPU to do so? And why we need to actually have this square upload and don't do it element by element is to have the memory coalescence, and then you have shared memory non-strided access to here. So this will most likely have the same speed as the just uploading the data to the GPU. So I have also a shader that performs just a memory transfer. One second. So this is an example of shader where you just copy data on the GPU and then write it out in the output buffer. And if we launch this too, we can compare how much time actually it takes the overall transposition on the shader and on the GPU. And if it's like really small, then this will be a bandwidth bound, memory bound problem. Otherwise, it will be a compute bound problem. So this is how we write the shader code on Vulkan. Well, this one is just ordinary GLSL code, but after you compile it, it will be translated to SPIR-V binary, which is used by Vulkan. So now we specify the application, which is using like 4K on 4K system, which will be transposed. We allocate buffers on the GPU. Here is a special routine I created. So these buffers are actually not host visible. So to transfer data to this buffer, we need to create a staging buffer, which will be host visible and will be done once before the application. So the application structure is actually something I like to do is just you have an application which has all the data related to the application, and then you have some GPU structure that has all the data related to Vulkan. So this application has pointers to the buffers you allocate. It has the specialization constants, which describe the shader dimensions and all this similar stuff. And then it has like sizes of a system you use. So let's continue. So then you create the application. This is the function which like binds descriptors. Descriptors is a thing that just makes the code understand that your shader uses this many buffers and creates the connections to it. So here I make a connection to the input and to the output buffer. And then you create your specialization constants, the constants that were used in shader, you can specify it here. Then you actually upload the code and like initialize the compute pipeline. The compute pipeline is a part which will be later used to make a dispatch and launch an application. Yes, it sounds really like confusing at start, but it's really streamlined logic which applies to every application in Vulkan. And in a similar fashion, it can be like translated to CUDA. Well, it has a little bit more boilerplate, but this is all like not really that hard. And you will have this example if you want to play with it and like just to follow what happens logically in the pipeline. Okay, so then you transfer data from the CPU. I have created a small function that can help with that. It just uses a like staging buffer. It allocates a special buffer which is host visible and then transfers the data to it. And then from this buffer, it's like performs an internal VRAM transfer, and then it frees the staging buffer used. The same thing is done when we want to download data from the GPU to the CPU. Actually, on integrated GPUs, all the memory is host visible, but we want to make code be able to run on the memories with its own dedicated VRAM. So we have this. Okay, now we do a run of the app, which is like a thing that creates a command buffer, which records a command buffer. So for example, here we create a command buffer, which will be executed on the GPU. And we like append the command which executes the transposition 1000 times here. So like there are no dispatch overhead, because like launching one command can take a considerable time. But if you write a bunch of them, then this will take more time to execute, but it will alleviate the startup of the Vulkan application. And the same is also true for CUDA codes. So the append app function is just appends to the command buffer. It writes the dispatch call, for example. It binds the compute pipeline we have created in its descriptor sets to the command buffer, and then it creates the dimensions used for a kernel. So for example, we need to do a 4K on 4K transposition, and we have a 16 on 16 size of our workgroup. So we specify the amount of workgroup, which will be like 4K divided by 16 on 4K divided by 16 here. And then we place a pipeline barrier, so the second dispatch doesn't like access the data before this one finishes, which like makes sure that there will be no race conditions. So we have done this, and then we performed the app, and we just we submitted it, and we measure time by just how much time it takes. And we place a fence, so after the queue, the command buffer has been submitted to the queue. When it finishes, we wait till it finishes, and then we measure time taken. So here we do so, and then we output the result, how much transposition taken and how much just data transfers taken, because here I've created an application that uses a shader for the bandwidth measurement, which like I have shown you before, two shaders. The first one is the transposition. The second one is the just memory transfer from one buffer to another. Then if you want, you can transfer data to CPU and print it out to see if your application has performed the transposition. Note that we perform transposition on the input buffer to the output buffer, and not do it backwards, so it will always do the same operation, because it will get the input buffer and write to output buffer. So no matter how much time you will get transposed result in output buffer. And then you need to free your allocated resources afterwards. So we have created this and built it. I have built it in release mode because I want full performance, and the debugging takes a little bit more time. Okay, and now I will just launch it. Here I have a GPU Z, which will show that we have 100% GPU load on the Intel iGPU, and 6 watts, which is probably something close to the maximum value of power you can get on the Intel GPU. Okay, so as we can see, we get transfer time is 8 milliseconds and transpose time is 8.8 milliseconds. So most of the time on the shader is taken by the transfers. So here you see the buffer. So 4K and 4K floats take 64 megabytes of DRAM on this Intel iGPU. And as it is Intel iGPU, it uses the same memory as the processor, which actually has the one installed in this laptop has 2134 megahertz and of SODIMM memory, which actually can transfer data maximum at 17 gigabytes per second. So the bandwidth measured is actually really close to the theoretical bandwidth you can get on the RAM on this laptop. And as you can see here, the overall time compared to the total transpose time is close to 100%, which shows that most of the time is taken by the transferring. So for example, now I will show how the things I've talked about during the presentation can affect this. So for example, 1 second. Here. We have 16 on 16 data transfers, which makes it coalesced. So there is 64 bytes of uploads. If we do a kernel of 8 on 8, which will correspond to 32 byte uploads, and launch it, oh, I don't think you can see actually. Yep, here. So you see 100% GPU utilization here. Wait for some time. Here, as we used the 8 on 8 buffer, the time has taken the time taken to do 1000 transposition is increased by 2, and the bandwidth is only 8 gigabytes per second. because the memory becomes non-coalesced. So I will launch again with 16 on 16 to see. So here you can also monitor the load. And here we get 16 gigabytes per second, which shows that Intel GPUs coalesce memory in 64 bytes. And if we modify this one, we reduce this one here, save it, and here we don't use shared memory, and launch it with this. So shared memory access becomes strided. We'll see like how much performance we lose in this case. It still shows 100% GPU load, but the accesses become with bank conflicts, and we expect to get really like performance degradation compared to the pure memory transfer. And as you can see, the transfer time is 8 milliseconds as it was before, but transpose time takes 2 times more time, and the total time to transpose time becomes really like comparable. So you need to maintain the bank conflicts. Okay, now I will briefly show the same code run on NVIDIA and AMD integrated GPUs. 1 second. Okay, this is a different laptop that has NVIDIA GTX 1660 Ti with Max-Q and Radeon RX Vega graphics. And you can specify for each application in NVIDIA control panel which GPU you want to use. Here it says that we use NVIDIA GPU. So here I have the same application built with 16-byte memory access. And if I launch it on NVIDIA, what we get is like 224 gigabytes per second bandwidth and like really good transpose time. The 1660 Ti has I think GDDR5X memory, and the bandwidth it has is 288 gigabytes per second, which is a theoretical bandwidth. So we also get really big bandwidth, really close to the actual theoretical bandwidth there. So for example, if in the control panel, I specify that I want to use integrated graphic card, it will use Radeon RX Vega 10, but I need to modify the value of transposition because it has its own dedicated graphics memory, and it's only 256 megabytes. So 64 megabytes is a really big part of it. Sometimes it can't allocate that much. So if I launch this now, okay, I think it's not using it. I forgot to apply. So now it will use the AMD GPU. And as you see on this one, the GPU is only 25 gigabytes per second because it's an integrated one. If you want to see which GPU is actually using, well, it's not implemented in this code, but okay, I won't just show it because, well, you can use my other code like fast Fourier transform library, and you can launch it with devices command and see which one is using. Or you can check it out here, like in GPU power set. So for example, you can check if your Radeon graphics supports Vulkan here. So During this coding section, we launched the simple transposition on 3 vendor GPUs on Intel, AMD, and NVIDIA. And we get like that Vulkan can actually reach the theoretical limits of this GPU if you optimize your code really well. And I also shown that if you write your code improperly and like invalidate and like use shared memory or global accesses wrongfully, the performance can really be degraded, sometimes like 2 times or even more. And this is why I say it's really important to understand what's happening in the GPU so your code actually can use its potential fully. So I think that's all I wanted to show during this coding session, and I would like to answer your questions now.
Thank you very much, Dmitrii, and big thanks for the code demonstration session. Guys, do you have any question for Dmitrii? And if so, please unmute and raise your question. Okay, I don't see any question coming. So I'll stop to record the video. Give me a sec.